I'm Whitney. Welcome to Wyzant's Getting Ready for Calculus. Thanks for joining me today. Today we'll be talking about limits. It might be a review from pre-calculus for some of y'all. For others, it'll be the first topic you guys go over in calculus. If you have any questions, please drop them into the Q&A chat and I will try to help you with answers. We should have time at the end for Q&A as well. Let's get started. Okay, so the first thing we need to talk about are limit notations. So you'll see it written as limit as x goes to a of the function, and then sometimes instead of f of x, you'll see the actual function there. You can see, sometimes you'll see limit as x goes to a from the right. This plus sign means right, or you can think about it as the positive x-axis, because that means it's coming in from the positive infinity side of the function. Or limit as x goes to a from the left. This negative sign means left of the function. Graphically, what we're talking about when we're saying that, let me get a little sketch here. Put some asymptotes on it. Okay, let's say that we have a function and asymptote there. Hole there. And okay, and for the sake of this graph, we'll put in points as we go. So if you were trying to find the limit as x goes to negative infinity of the function, what that means is you're trying to find x going to negative infinity. So you're following along this line all the way until you get to negative infinity. You can't actually get to negative infinity, so that's why we're thinking about like what it's approaching. And if you look at the blue graph, as we go to further and further negative x-axis, x points, the y value is going to this orange dotted horizontal asymptote. So let's say that this was at 3, then our answer would have been 3. If we're trying to find the limit as x goes to, let's say that this is at -4. So at -4, you can't really say what it goes to because from the left side, it's going to positive infinity, but from the right side, it's going to negative infinity. So if I had said from the left of the function, then that's going to positive infinity. But if I had said limit as x goes to -4 from the right of the function, that's going to be going to negative infinity. So it's really important that you specify which side you're talking about if it goes to different functions, because in order for it to be, as it goes to -4 to work, it has to match on the left side and the right side. So these two numbers need to be equal, and then that's what it would be here. But since they're not equal, we're just going to write D and E for does not exist. What do you think the limit as x goes to, let's call this -2 is from the left? So here, we're coming in from the left. Let's call this -1. And we'll call this -2. So as we come in from the left, we're following this line this way. We're approaching this bubble. Even though the actual filled-in point is up here, we're actually approaching -1 for the y value there because of that bubble. And then limit as x goes to -2 from the right of the function. Now you're following this in from the right side, and you're going to hit that bubble here. You're still approaching the y value of -1. Okay, so because those match up, then I could have also said the limit as x goes to -2 without left or right of the function is also equal to -1. Now, if I had wanted to say the limit as, or if I had said actually f of -2, now f of -2 is going to be the y value where it's actually filled in at. So that's going to be +2. This would not be considered continuous because the limit doesn't equal the function at that point, but we'll talk about that later. Okay, So what do you think the limit as x approaches, let's call this +3 of the function is? So you'd want to check both sides because it wants just 3. It doesn't want from the left or from the right. So we need to check, make sure both sides match. And then if they match, we can give an answer. Otherwise, we have to say does not exist. So from the left side, we get +∞ because our y value is going to +∞ there. Or from the right side, we're going to get +∞ for the same reason. What about the limit as x goes to +∞ of the function? So here you can only really come in from the right, so it's understood, or from the left, so it's understood that you're coming in from the left here. But you can kind of see that as it gets to here, it's going to that horizontal asymptote, -2. So you're only going to have a limit as it goes to +∞ or -∞ if you have a horizontal asymptote. If this had shot down and gone to -∞, you wouldn't have, you would just say does not exist because it's not really approaching anything. Or you could say -∞. Okay, so in summary, holes, it's all about what it's approaching, not about what the actual value of the function is. Limits are all about the approaching. All right, let's try to do another example that's kind of similar. Let's say we have -3, -2. Oh, let me space that out a little more, sorry. 2, -1. Okay, so let's say that we have our function and let's say it's filled in here. It's gonna go up to here, open circle at -1, drops down to here. We're gonna fill that in. Okay. So for this one, if I want to find the limit as x approaches -3, I can't really do that because it doesn't approach the same thing from the left and the right. From the left, it doesn't exist because you're not following, because there's just no function over here, right? The line segment doesn't start till -3. But I could say from the right side. So from the right side, we're approaching 0 because we're coming in on this. And then also if I had said f of -3, that would have also been 0. For if I wanted to say limit as x approaches -1 from the left of the function, what would that be? So you're looking at -1 is here. So if you're coming in from the left side, you're approaching this bubble at 2. And then if I had done limit as x approaches -1 from the right of the function, that one's going to come in from this way and you're going to approach +1. So that means that as we just approach -1 for the function, it does not exist because those 2 and 1 don't match each other. But then if I had said f of -1, that's talking about where it's actually filled in at, and I get +1. Okay. Limit as x goes to +1 from the left. And we're going to get the limit as x goes to +1 from the right of the function. So from the left, we're coming into -1. From the right, we're coming into +1. So that means the limit as x approaches 1 of the function also does not exist. And here, f of 1 would also not exist because it's not actually filled in anywhere on this vertical line. There's no hole that, or there's no spot that's circled in. Okay, I'm gonna give you a second to kind of break that down before we move on to figuring out limits algebraically. Okay. Now, if you're given limits and they're given to you algebraically, so like something like this, as it goes to -2 of 4x squared plus 6x minus 9. Your first step is just to try to plug it in. If you can plug it in and you get an answer, that's your answer. So here, 4 times -2 squared plus 6 times -2 minus 9. There's nothing wrong with plugging it in that way. If we do that, we should get 15. If you're given something like this, where you're going to have a 0 on top and bottom when you plug in your thing, that's going to be an indeterminate form. So we're going to have to do a little bit of extra work to see if it's, even though the function doesn't exist there, if it's approaching anything there. So because this term and this term can cancel out, we know that that's a hole from pre-calculus. So what you can do is then plug in. It's totally okay to have a hole at that point, but the limit will be whatever you get after you cancel out the hole. So if you plug in -3, you get 2 over -1. So your answer would just be -2 for that one. The actual function there at -3 doesn't exist though because of that 0 in the denominator that you originally had. Let's try another one. Let's say limit as x goes to 1/2 of 4x squared plus 4x minus 3 all over 2x squared plus x minus 4. It's very good to brush up on your factoring by grouping or doing the guess and check method, or however you learned how to factor for this unit, because you're going to be factoring a lot. It's also really important to rewrite the limit each time. So what we could do is we could try to split this up. 4x, you have two kind of ways if you're going to check it. You could do 2x and 2x and see if there's something that you could put there. Or it might be a 4x and an x, and then see what you could put there. This one, if you go through the steps, you're going to get 2x plus 3 and 2x minus 1. And then on bottom, if you do the same thing, you'd get 2x minus 1 and x plus 4. Okay. So when you plug in 1/2, you still get that 0 there, but because the 1/2 will cancel out, you're able to just plug into the next step. So we would get 1 plus 3 on top, so 4. And on bottom, we'll get 4.5. So that's just going to go to 8/9. Okay. Other things that we'll run into are if you have square roots, you want to be careful because you can't plug in a negative into a square root. If you had something like this, though, first step, always just plug in, see what you get. So when I plug in 4 to the top, I get 0. It's okay to get 0 on top as long as we don't also get it on bottom. So on bottom, we'll get an 8 here. That just goes to 0. There will be other circumstances where you get 0 on top and bottom, and we're going to have to deal with something else with the square root. So for like example, let's see, if we're going as x goes to 0, we have root x plus 3 minus root 3 over x. Now when I plug in 0, I get square root 3 minus square root 3 on top, which is 0, and I get 0 on bottom. So that we're going to run into an issue. And the way that we get rid of it is actually using the conjugate, or multiplying by the conjugate. So you probably remember that from imaginary numbers to get rid of the I. So this one, the square roots are issue. So what we're going to do is we're going to multiply by x plus 3, change the sign in the middle to plus root 3, and we have what we do to top, we have to do to bottom. Okay, so when we multiply this out, we'll get, let's see, this is difference of squares. So you could FOIL it all the way out, or you could use the fact that a minus b times a plus b goes to a squared minus b squared. So this is going to go to x plus 3 minus 3. And then the bottom, I wouldn't bother factoring out because it'll end up canceling out, usually. So like here, we get an x on top and an x on bottom. And we can cancel out those x's, and that'll cancel out the issue that we were having with the 0. So then now when we plug in 0, we're going to get 1 on top and root 3 plus root 3 on bottom. So just 1 over 2 root 3. All right, let's look at some more problems. What if we were doing limit as x goes to 4 of x squared minus 16 over x minus 4. So same thing, we run into 0 over 0, so we could try factoring out. We'll get x plus 4, x minus 4 over x minus 4. We want to rewrite the limit next to it because we always want to do that. So then now, after we've canceled out, we can plug in 4 and we're just going to get 8. If there are no x's when you're trying to take a limit with respect to x, your answer is just going to be whatever that constant is. So here, the limit as x goes to 2 of the function 6 is just going to be 6. And if you think about like what that line represents, as you go over to 2, you should still get a y value of 6. All right, let's do some piecewise functions. Let's say we have a function, and that function is x minus 5 over x squared minus 25, where x does not equal 5. And then let's say it's 5 where x is equal to 5. And say we're trying to find a couple things. So we want to find the limit as x approaches 5, and we want to find the function at 5. So the limit as x approaches 5, that's going to come from when we take the limit where it's everywhere but 5, because for limits, you only care about approaching, you don't care about that actual value at 5. So this looks kind of similar to the one that we did here. We're just going to factor the bottom. That bottom is going to factor to x plus 5, x minus 5, because it's a difference of squares. And then our minus 5s cancel out, so we just get left with 1 over x plus 5. So we're going to get 1/10. And then here, f of 5 is going to be 5 because that's where it's actually filled in at. Okay, let's do some one-sided limits. So let's algebraically. So we'll do another piecewise. This time we'll have 6x minus 4, and let's do 4 minus 6x. This is where x is less than or equal to 2, and this is where x is greater than 2. So we want to find the limit as x approaches 2 from the left, the limit as x approaches 2 from the right, the limit as x approaches 2, and then the actual value of the function at 2. And we need these f of x's next to all of our limits. Okay, so if we're approaching 2 from the left, that means that we're on the left side of the graph, so we're less than 2. So all we have to do for this one is go to that function where we're at when we're on the left side of 2 and plug in 2 there if we can. If you can't, then you'll probably have to do something like what we did with the square roots or factoring or something like that. But here from the left, when I plug in 2, I'm going to get 12 minus 4, so 8. From the right, that's where x is bigger than 2, so I'm looking at the x is greater than 2 side, and I'm going to get negative 8. Because those don't match, does not exist, but if they did match, it'd be whatever they both were. And then f of 2, I'm looking for where the equal sign is. So here the equal sign is on this function. So I'm going to be plugging into this guy again and get 8. Right. If all 3 of these, or all 4 of these things matched, we would call it continuous. Okay, let's do another example. Let's say g of x is 3x plus 1, 7, and x plus 5. Let's say here this is x is greater than 2, x is equal to 2, and x is less than 2. So we're going to find the same exact thing. We want to find limit as x goes to 2 from the left of the function, limit as x goes to 2 from the right of the function, limit as x goes to 2 of the function. And then we also want to find the actual value of the function at 2. Okay, from the left, that's less than 2, so we're going to plug into there, so that's 7. From the right, that's greater than 2, so we'll plug into the top one, so that is also 7. Here, the limit as you actually go to 2, so that's if these two things are equal to each other, then it drops down. So they're both 7, so our limit as x goes to 2 is 7. And then for the actual value of the function, that's looking at this guy, so that is also 7. Okay, so this one we would say is a continuous function. For limits, when you have absolute values, you're going to want to make your own piecewise function. So let's say that we had a function of 4t minus 8, the absolute value of that. So my first step would be to think about it in terms of piecewise. So the breaking point for this absolute value is t is 2. So I want to think about when t is greater than 2 or when t is less than 2. And one of them can be equal. It doesn't really matter which one, but we know this is a continuous function. So if your t's are greater than 2, so if you're plugging in something like 3 or 4 or 5 or 100 into this function, you're going to get a positive on the inside. So the absolute value doesn't really do anything. It just kind of acts as a parentheses. Where t is less than 2, you're plugging in something smaller than 2 here, so maybe like 1 or negative 100 or negative 2000. And on the inside, you're going to get a negative, but the absolute value is going to make it positive. The way it does that is by multiplying by a negative sign. So you could rewrite this as negative 4t minus 8. So if you take the limit as t goes to 2 from the left of this one, you're looking at this function. If I plug in 2 there, then I'm going to get 0. Same thing if I did as t goes to 2 from the right. I'm using this side, and I'm going to get 0. So then that means the limit as t goes to 2 of the function is 0. Let's look at one that has an absolute value but is a little bit more complicated. So let's say that the limit as x goes to 0, and we'll do the absolute value of 5x over x. We'll do the same first step. So we're going to split the function into a piecewise. We're going to say if x is greater than 0 and x is less than 0. This function is not actually defined at 0 because if you plug in 0, you're going to get a 0 in the denominator. So when you're plugging in x is greater than 0 to here, if I plug in a positive number, 5x is going to be a positive number as well. So just like the last one, that acts as a parentheses. So it's going to be parentheses 5x over x. But if I plug in a negative number, it's going to be negative inside here. So then the absolute value acts as a negative again. So negative 5x over x. Now, because these are parentheses, it's totally fine for me to just cancel out those x's because there's one on top and one on bottom in each term. So now if I'm finding the limit as x goes to 0 from the left of the function, on the left I'm less than 0, so I'm going to get negative 5. So the limit as x goes to 0 from the right of the function, I'm going to get positive 5. Those don't match, so the limit as x goes to 0 of the function is equal to d and e. And then also we know that f of 0 is d and e because we have that 0 on bottom here in the initial function. Okay, let's see. Let's look at one where you're still going to have an x is 0 on bottom even after we cancel. So your first step always is going to be to factor out as much as you can and see if you can cancel anything after you've plugged in and you come to an issue. So here, when I plug in, I get negative 16 on top, but I'm going to get 0 on bottom. I think it might be easier for us to factor out, so let's do that first. You don't technically have to do it, but it'll make it a lot easier to work with. So we can pull out a 2x on bottom, and we'll get 2x squared minus 1. So if we wanted to simplify that on bottom, we could change it to root 2x minus 1 and root 2x plus 1, but I don't think that makes it look any nicer. So because it's a 0 on bottom but a number on top, it's going to go to an infinity. We just need to decide which infinity. And the way we're going to do that is by looking at from the right side and from the left side. So we're going to branch off, and we're going to think about the limit as x goes to 0 from the left of x plus 4, x minus 4, over 2x squared minus 1. So when I plug in 0 from the left, I'm plugging in 0, but I'm plugging it in on the negative side. So I'm plugging in a negative, really, really small number. So on top, the negative, really small number is not going to affect it very much. I'm still going to get negative 16 on top. But on bottom, when I plug in 0, this becomes a negative 1. But this is going to become a very small negative number. So I'm going to think about it as being like a negative 0. So it's 0 on bottom, but it's a negative times a negative, so it's like a positive 0 on bottom. Because of that negative on top, it's going to go to negative infinity. Okay, so that probably seems pretty confusing right now. Hopefully when we do the next problem, it'll make a little more sense. So let's say we go 0 from the right. So we'll do x plus 4, x minus 4, 2x squared minus 1. Okay, so we're still getting negative 16 on top. That's not changing just because we're plugging in a little bit of a positive 0. On bottom though, this is going to be a positive 0 because I'm plugging in a little bit to the right of 0, so like 0.001. And over here, this is still going to be a negative 1 because this is still going to be much smaller than that negative 1. So I'm getting a negative 0 on bottom, so it's going to go to a positive infinity because these are going to cancel out. Let's do one more of those just to kind of solidify it. Limit as x goes to 6 of 1 over x minus 6. This is another one where we're going to get 1 over 0 or a number over 0. So we know it goes to positive or negative infinity. We just have to check which one and see if they match. So if I do limit as x goes to 6 from the right, when I'm plugging in 6 from the right to this guy, I'm getting a positive 1 on top, but I'm getting a little bit bigger than 6 on bottom, so I'm getting a positive 0, so it's going to positive infinity. When I plug in from the left, though, I'm plugging in a little bit smaller than 0, so I'm going to get a negative number on bottom. It's basically 0, but it's a little bit of a negative, so I'm going to get negative infinity. So if I had just asked about the limit as x goes to 6, I would say does not exist because these are different answers. There will be some cases when it will work out. So like had this been squared, then this would have been positive infinity because you would have got a positive 0 squared as a positive 0. But this would have been a negative 0 on the inside squared as a positive, so it would go to positive infinity. Okay. Let's do, we only have a few minutes left. Let's talk about the table method of finding them. So this one you can always do if you have access to your calculator, but it takes a lot longer. So it's much better to get a little more intuition with the way that we were doing it before. This is if I was trying to find the limit as x goes to 0 of sine. And let's actually, instead of sine of x, let's do sine of 4x over 4. So because I want to go to 0, I want to pick numbers that are really close to 0. So maybe I could put negative 0.001, negative 0.01, and negative 0.1. And then on the other side, you'd have just the positive versions. So you just want to get increasingly closer as you come in this way. And then all you're going to do is you want to make sure your calculator's in radian mode because usually when we have signs and it doesn't specify, we want it to be in radians. And then you will just go through each one and kind of compute it. So if I did sine of 4 times negative 0.1 over negative 0.1, I would get, let's see. So this gets me, you want to write out a few digits, so 3.894. And then if I did it with an extra 0, I would get 3.9989. And then with one more zero, I'm getting 3.999989. So it gets closer and closer, and we can kind of see that it's approaching 4 from this way. And what's actually going to happen on this side is it's also going to, if I fill in those digits, it's also going to get closer and closer to 4 this way. So that tells me that this limit goes to 4. If it approaches a different side on the left and the right, then I would know that it does not exist. This is actually a really important one that you want to know. So you want to know that the limit as x goes to 0 of sine. And then if there's any kind of constant here, cx over x is going to go to just c. The other one that's kind of similar is as x goes to 0, 1 minus cosine of x over x is going to go to 0. And you could check that the same way with that table method. All right, so we're at the end of our time for today. Do you guys have any questions? Feel free to shoot them in the Q&A, and I will try to get to as many as I can. Okay, it looks like we don't have any questions coming in. So just to wait another second for a question to pop in, let's talk about continuity and the rules for it. So in order for a function to be continuous, the first thing is that the limit has, as x approaches c of the function, has to exist. That's kind of its own little blurb in itself. So that's kind of what we were talking about for most of today, is that the limit as x approaches c from the left of the function exists. The limit as x approaches c from the right of the function exists. And the limit as x approaches c itself exists. So more or less, it's just the limit as x approaches c from the left has to equal the limit as x approaches c from the right. The second tenet is that f of c has to exist. So that means it actually has to be filled in somewhere. You can't just have a hole. And if both of those things are true, they also have to be equal to each other in order for it to be continuous. Has to equal f of c. So basically, the first one says that you have something that looks like this. You're approaching the same thing from either side. Second one says that you fill in a point somewhere, and doesn't really specify that you fill in the same point. And then 3 says that that point that you filled in has to be where that hole was. All right, awesome. Well, thanks for joining today. Have a great weekend.